This is Griffiths Electrodynamics, problem 2.12. Use Gauss's law to find the electric field inside a uniformly charged solid sphere, charge density rho. Okay, alright. So we're going to use Gauss's law, which this tells us that if we integrate the electric field around a closed surface, and I guess pick out the normal component of it with this dot product. So we dot it with the little differential area vector pointing outward from the surface, then that integral will be equal to the charge enclosed divided by the permittivity of free space. Alright, so what we have here is a solid sphere charge density rho. So right off the bat, if we were to surround this entire sphere with what we call a Gaussian surface, the total charge enclosed is going to be the charge density multiplied by the volume of this sphere. So the enclosed charge is equal to the charge density multiplied by the volume of a sphere, 4/3 pi r cubed. And let's just see, it doesn't tell us, the radius, it doesn't tell us that it's A or something, so for now we'll just leave this as R. So for right now, this R is referring to the radius of this sphere. Okay, that is kind of confusing, but alright, now by symmetry, this is a spherically symmetric situation, so we can use the Gauss's law trick, where if we do this whole integral out, we get the magnitude of E, and it's just the area. And basically, because of the symmetry, E is constant, and it can be, the magnitude of E can be pulled outside the integral. Then we're just doing an integral over the surface area of a sphere, and so for the integral, we're going to just get the total surface area of a sphere, which is 4 pi r squared. This. All right, and we also know that for rho, if this is a positive number, if this is positive charge that we're dealing with inside the sphere, then the electric field vectors are all going to be pointed out radially. So right now we're solving for the magnitude, but when we go to get the vector from that, we know which direction it's going to point. It's all going to come. So once we find out what this magnitude is here, we're just going to tack on a little r hat vector to show us the direction of this, which we got from symmetry. All right, back to this. So we had this answer for this side of the equation. Again, because of symmetry, E was able to come out, integrated over the surface area of a sphere, and here we go. Now we need this side of the equation, and this is just this, but just divided by epsilon naught. All right. Okay. Well, this is great because these 4's are going to cancel, and so are the pi's, and this r squared will cancel with 2 of the r's in the r cubed, and we only have 1 left. So when all the smoke clears, we only have this 3 down here and this r. So we have a rho r over 3 epsilon naught. Okay. All right, so now we know what the magnitude of E is. To save space, I'm just going to put this equation right here. So now that we have this E, we know that in order to get the vector electric field, all we do is tack on the r hat. Right, so a radial electric field, and then this is the magnitude of it. If rho is positive, so if it's a positively charged sphere, then we go outwards in the positive radial direction. If rho is negative, then it will point inwards. We get a minus sign up inside of this rho, and we get a minus r hat, so everything's pointed inward. Oh yeah, and it says compare your answer to problem 2.8. Well, obviously we're going to get the same answer, but 2.8 is a different problem which we may cover in a different video. And according to 2.8, in order to do that one, you have to do 2.72. So 2.7 also, I guess you could say. Rather than do 2 extra problems right now, we'll just call this video good, and we'll trust that yes, you do get the same answer from problem 2.8.